The next data structure we're going to cover is the hash table. It's a powerful and widely used data structure. You'll find it appearing in different forms like hash maps and hash sets. To understand the core idea, let's think of an apartment building. If I know that my friend lives in apartment 406, I can easily go up to their apartment. If I have the key, aka the apartment number, I can easily find the associated value, my friend's home. Without the key, I would struggle to find my friend's home, and my best bet would be to visit every single apartment in sorted order until eventually I hit my friend's home, but that's ineffective. Let's look at two common hash tables. We have hash maps and hash sets. Hash maps store a key value pair. In our example, we had the apartment number, which was the key, and my friend's home, which was the value. Hash maps are used to find detailed information about something, whereas with hash sets, we're only storing the key. You don't have any associated values. Hash sets are used for lookups to check if an element is part of a set. Think of a bouncer with a guest list at a party. The bouncer only cares if your name is on the list, not any extra information about you. Hash tables generally have three operations: insert, delete, and search. For a hash map, you would have insert to add a key value pair. The equivalent for a hash set would be inserting the key. For a hash map, deleting would be removing a key value pair, whereas the equivalent for a hash set would simply be deleting the key. For a hash map, you would have the search function to find a value using its key, whereas for the hash set, you're simply checking if a key exists. All these operations take, in an average case, big O of 1, or constant time, meaning whether there's one input or a million inputs, the functions will always take the same amount of time. There is a caveat for this, but I'm going to hit that a little bit later. Let's take a look under the hood for a hash table's operations, right? Under the hood, a hash table actually uses an array. So for the hashing process, what happens is you take a key, you pass it into a hashing function. That hashing function maps to an index, and then you can use that index to then connect it to an index in the array, and then you would store the key value pair within that index space, right? In this example, we are going to be using fruits as the key and then the price of the fruits as the value. So we have apple. We are going to pass it into the hashing function. For now, we are going to keep the hashing function as a black box, just so we can understand the basic concept. Apple, let's say, is the index 2. So we go to index 2, the value stored is apple, and then the value is $1.50. For banana, we pass it into the hashing function. It's going to map to index 9. So the key is going to be banana, and the value is going to be 75 cents. We have orange, pass it into the hashing function. We get index 0. orange is mapped to index 0 with key orange and value $2. This is why all operations are, in theory, big O of 1 or constant time, because we should be able to get the index in constant time, and then we can directly access the key value pair within the array. A note that I would like to make is that both the key and value are not limited to being a string or an integer. They can be complex objects, and the hashing function should be able to take in any key and output a valid index. Before we break down how hashing functions actually work, I want to review modulo operators as they are used within a hashing function. So a modulo operator, often shown as a percentage sign, finds the remainder after division. So in this case, we have 17 mod 5 gives us a remainder of 2. One way you can think about this is in terms of cookies. Let's say you have 17 cookies and you have bags that can hold at most 5 cookies. You want to see how many cookies are left after filling as many bags as possible, right? So we take our first bag, we fill in 5 cookies. That leaves us with 12 cookies, so that means we have enough to fill another bag. We fill in another 5 cookies. We're left with 7 cookies. That means we have enough to fill another bag. We're left with 2 cookies. 2 cookies isn't enough to fill a whole bag, so that means 17 mod 5 leaves us with 2. Another way you can think about this is through the use of a clock. Imagine that it's currently 9 o'clock, right? It's currently 9 o'clock. And you know that you need to see your friend in 6 hours. So 9 plus 6 equals 15. But our clock only goes up to a maximum of 12. So what does 15 hours really mean? Well, let's see. If we were to go 6 extra hours to 10, 11, 12, 1, 2, 3, we get to 3 o'clock. Well, this is essentially what the mod is saying. 15 mod 12 gives us 3. It's essentially telling you where you will land after you wrap around a certain number. That certain number being 12, we took 1, 2, 3 steps. There are many valid ways to implement a hashing function, but we're going to look at a simple method. For keys that are strings, we could convert each character to its ASCII value and then sum them up to get an integer, right? So what is an ASCII value? We have a standard where every character has an associated value. So our lowercase o has an associated decimal value of 111. Our lowercase a has an associated value of 97. So let's look at our example, orange. O has an associated value of 111, R has an associated value of 114, A has an associated value of 97, N has an associated value of 110, G has an associated value of 103, and E has an associated value of 101. If we sum this all together, we get 636. But we see that our array has a capacity of 12, right? So 636 is not a valid index. So what would we do? We would use the modulo operator with the array capacity being 12. This results in index 0, and that's why we store orange at this index. Let's try one more example. Let's try mango, and let's have it with a value of $1.50. Oh, all right. M has a value of 109. Lowercase a has a value of 97. Lowercase n has an associated value of 110. G has 103, and O is 111. You sum it up and you get 530. Mod it by the capacity of the array being 12, and you get 2. Uh-oh, we already have a key value pair stored at index 2. So we don't want to override this and lose the data associated with Apple. This is a collision. A collision is due to our hashing function having a poor distribution. But don't worry, there is a solution around this. There are two ways to address collisions, either using separate chaining or open addressing. For separate chaining, what we do is add an index. Instead of storing a single key value pair, we store a linked list where each node in the linked list contains a key value pair that is associated with that index, right? So we have Apple, it's stored at index 2. We have orange, it's stored at index 0. And then we have banana, it's stored at index 9. That's where the node is, right? But what happens for the collision with mango? We also know that the hashing function results in index 2. So what we would do is we would go to index 2, make sure that our linked list doesn't contain the key mango already, right? And then we would create our node, mango. It has a value of $1.50. We would set next for our new node as the previous head, and then we would update the index to set the head as our new node, right? This is great as an index can hold multiple nodes, right? But the issue that arises is as the linked list gets bigger, the efficiency is going to tank. So imagine you have a horrible hashing function that results in the same index for all nodes in your hash map. So over here, orange no longer points to index 0. It's going to also point to index 2. Same thing with banana. It's going to point here. Right? So imagine our hashing function was horrible. It had a horrible distribution. It said every single node is stored at index 2. So if we wanted to search for banana, we would go to index 2 because that's what our hashing function resulted in, and we would have to traverse every single node until we hit banana. What happens if we wanted to delete? Again, we would have to go to the index that resulted from the hashing function, go and find our node, and then we could delete banana, right? So in this scenario where your hashing function has a horrible distribution and all your nodes are within this linked list at index 2, your insert, search, and delete operation all have a time complexity of big O of n, because in the worst case where you want to access banana, you have to traverse every single node before banana. So that means every single node within your hash table. This is why the time complexity would be big O of n in the worst case. In reality, when we are talking about hash tables, we always go with the average case, big O of 1, or constant, because we have access to some amazing hashing functions that result in great distribution. We also use the concept of load factor. So let's say you set your load factor to be 50%. That means once your indexes have hit 50%, once you've used 50% of your indices, you can then resize your array. So initialize a new array, double the size of your original, and then rehash every single node. So even though mango would have been at index 2 in the previous hashing function, maybe in this new array with this new capacity, it's actually at index 15. The other solution is open addressing. This solution basically says if you get to an index you're supposed to be at and the space is already taken, then find an empty one, right? There are multiple ways you can go about this, but mango is supposed to be at index 2, but the space is taken. So one way you can deal with this is linear probing. Linear probing says keep incrementing the index by 1 until you get to an empty space. So 2 plus 1 gives you 3, the space is empty, so we can insert mango there. And you get your value of $1.50. So then once you want to search for mango, you would once again go to the hashing function, it gives you 2, and then you would keep incrementing the index until you get to a space where the key matches up, right? Another solution, instead of doing linear probing, is using quadratic probing. So you get a key, you have mango as your key, you get a index of 2 from the hashing function, you square it, and you keep squaring the index until you get to an empty space. So 2 squared would be 4, the space is empty, so you can insert mango there. Mango value $1.50, and then if you wanted to search, you would pass the key to the hashing function. It gives you an index of 2. The key doesn't match, so keep squaring the index until the key matches. 2 squared is 4, the key matches. You do have an issue with open addressing, and that's clustering. That happens when you have a poor distribution with your hashing function where every key is getting mapped to the same index, right? So imagine orange is mapped to index 0. We insert it. We get banana, it gets mapped to index 0 again. We use linear probing to move it down to index 1. We have apple, it's mapped to index 0. We use linear probing. Index 1 is also full. Index 2 is empty, so we can place it there. Let's think about what's actually happening when we insert mango, right? So we get mango, it's mapped to index 0. We use linear probing, move down to index 1, it's still full. Move down to index 2, it's full. We move down to index 3, it's empty. We can insert it there. What did we actually do? We had to move through every single node within our map until we could insert. because our hashing function has such poor distribution, right? So that means when we want to now search for mango, we get a index 0 from the hashing function. We see that the key doesn't match. Use linear probing, key again doesn't match. Use linear probing, key doesn't match. We move one more index down. Finally, we get to index 3 and the key matches, right? This would happen for insert, search, or delete. When you have a really poor hashing function for open addressing and you get the same index popping up over and over, in the worst case, you're going to have a big O of n time complexity, meaning that you're going to have to go through every single node in your hash table before you can actually complete your operation, right? In reality, we don't actually say that the operations for a hash table are big O of n, regardless of whether they're open addressing implementation for collision or separate chaining implementations for collisions or handling collisions. We say it's big O of 1. We go with the average time because we have some amazing hashing functions in reality that distribute the indexes really well. We also implement array resizing once we hit a certain load factor, right? So let's say our load factor was 50%. If 50% of our indexes are used, then we can create an array of twice the size of the original and then rehash all the key value pairs. So even if Apple had an index of 2 from our previous hashing function, it may now result in an index of 15, right? Let's go over the implementation for a hash map using separate chaining as a response to collisions, right? So we have a class node where the constructor passes in key and value. We're going to initialize the key value for that node, and the next and previous pointers are going to be pointing to null initially, right? For the hash map class, we have the constructor and we pass in capacity. We are going to initialize our array of that set capacity, and each index is going to be initialized with a value of none or null, meaning that they are going to act as our respective head pointer for each index, and at initialization they're pointing to null, right? We have the capacity for the array, and then cur size is initialized to 0. It's going to keep track of how many elements we have in our hash map. The hash function is going to pass in a key. We're going to check if the key is an instance of a string. If it is, go through each character and sum up their ASCII values. Take that sum and mod it by the capacity for our array. That will result in the index to be used in our array, right? If our key is not an instance of string, we're going to assume that it's an integer. Take that integer and mod it by the capacity for the array. This hash function is a very simple hash function, and it doesn't have the greatest distribution since we're only taking the key and modding it by the capacity of the array. Another downside for this function is it only takes into consideration a key that's a string and a key that's an integer. But as we've said previously, keys and values can be complex objects. For the search method, we pass in the key parameter. We're going to get the associated index using the hash function. We're going to look at the head node within that index, right? We are going to then traverse through that linked list. We're going to say, while we still are at a node, we're not pointing to null. We're going to check if the current node's key is equal to the key that we passed in, then return that node and do whatever you want with that node. Otherwise, move to the next node in the sequence. If you get to a situation where you've traversed every single node in the linked list and this line never passes as true, then you will get to a situation where you've exited the while loop and you would have never encountered that key. So the key doesn't exist in the hash map, so raise the exception. For insert, we're going to pass in the key and the value. We're going to see if the current size divided by the capacity for the array, is it greater than 0.75, greater or equal to 0.75? Have we hit our load factor? This is what our load factor is. Our load factor is 75%. So do we have more than 75% of our hash map used so far, right? If we do, then we need to resize our array. Otherwise, get the index associated with that key, go to the head node within that index, right? And then traverse that linked list. While you traverse that linked list, see if you get to the current node and the current node's key is equal to the key that we passed in, then update that node's value to be equal to the value that we passed in, right? And then return. Otherwise, keep moving to the next node in the sequence, right? In the situation where the key doesn't exist in the linked list, create a new node, go to the head node within that linked list, and see if your linked list is not empty, go to the head node, right? Current head node, set its previous value to be equal to our new node. Then set the new node's next value as the current head. Update your index such that the new head is our new node. And then finally increment current size. Before we get into the delete method, I want to go over how it would look like visually because it is a little bit hard to follow if you're just looking at the code. Imagine we wanted to delete the node associated with key X, right? What we would do is we would take the key, run it through the hashing function, and get the index. Now that we're at the index, we would traverse the linked list to find the node with the associated key X, right? In this case, we would hit it over here. So we're going to keep a pointer right there, node to be deleted, right? Then we would once again take the key, run it through the hashing function to get the index, but this time we wouldn't traverse. We would simply be interested to see what the head node is. In this situation, the head node is pointing to the same node as node to be deleted, in which case we know that we're deleting the head node, right? So what would we do in that case? We would go to the node to be deleted, right? We would go to the next value. This next node is going to now be our head node, right? So update head to point to the next node in the sequence. And we would go to the node to be deleted. We see that its next pointer is not pointing to null. So what we would do is we would go to the next node in the sequence, y, and we would update its previous pointer to now point to null. And then for our purposes, this node is treated like it doesn't even exist anymore. Let's say we wanted to delete the node associated with key y. What would we do? We would use the hashing function to get the index. It's at index 2. We would traverse the linked list until we hit the node with value y. So we go to next, we finally hit it. We're going to keep track of this node. This is the node to be deleted, right? We would once again use the key, run it through the hashing function to get the index. We want to check the head node. The head node is this node, which is not the same as the node that we are trying to delete. So we are not deleting from the head. So what would we do now? We would go to the node to be deleted, right? We would go to its previous node and set its next value as the next value for our current node to be deleted, right? So for node X, its next value is no longer going to be Y, it's going to be Z. Then we would go to the node to be deleted's next value, right? And we would update its previous. Instead of pointing to y, it's going to point to what y's previous is, which is x. Right? And then for our purposes, this node acts like it doesn't even exist anymore. So, now that we've covered that, let's look at how it looks like code-wise. For the delete method, you have your passed-in key. You're going to search for that node associated with that key. Then you are also going to get the index associated with the key. And if the node to be deleted is equal to the head node, then you are going to update the head to be pointing to the node after the node to be deleted. If the node after the node to be deleted is not null, that means you have a valid node, in which case update that node's previous value to be equal to null, right? In the situation where you are not deleting the head node, right? This line failed, then you would enter this situation, this else statement. You would go to the node to be deleted, right? Its previous value, its previous node, that previous node is going to now point to, for its next, the node that comes after the node to be deleted. Then, if you have a node that comes after the node to be deleted, so it's not pointing to null, then you are going to update it, right? That node, its value that it points to previously, right, is going to now be equal to the node prior to the node to be deleted, right? In both of these scenarios, once the node is deleted, you are going to decrement current size. We move on to the resize function. Over here, we are going to store what our array currently looks like. We are going to update our capacity to be twice what the original capacity for our array was. We are going to set our array to be null. Every index is going to have a value of null, and it's going to be of size capacity, so twice what our original was. And then we're going to set the current size equal to 0. We are then going to go through every single index in our old array, right? We are going to traverse the linked list at each index, and we are going to rehash our key value pairs to be inserted into our updated array. So that is a wrap on hash tables. By the end of this video, you should be able to define common forms for a hash table, the main operations of a hash table, how arrays are used under the hood, how simple hashing function could be implemented, what are collisions and how they happen, visualize and implement separate chaining, as well as the issue of large linked list, visualize open addressing and using linear or quadratic probing, as well as the issue of clustering, and finally the average versus the worst case scenario for the hash table operations and why we generally consider the average versus the worst time. In the next video, we will cover trees.